Hello there! How big is Auraxis? That might seem like a simple question, but it actually ended up being more complex than I thought. So let's dive in. I found two ways to answer that question. So two ways to estimate the radius of Auraxis. We will look at both in this video. We will start with the simplest one, pulling information directly from Planetside to itself. When looking at the WarpGate terminal, we are presented with a view of Auraxis and its various continents. Conveniently, Hossin is at the equator. So all we have to do is measure how large Hossin is and apply that measurement to the image of Auraxis. Measuring Hossin from west to east, we get a width of 7.4 kilometers. Coming back to the image of Auraxis, we then only have to evaluate how much width Hossin takes up compared to the width of the visible hemisphere, and then a simple cross product gives us a diameter of the planet. Quick side note though, here I am assuming that the diameter of the circle is the diameter of the planet. But that isn't completely true, because what we see on this image is not an entire hemisphere, it's actually a bit less. That is due to the problem you can look up under the terms spherical cap. The hemisphere would be entirely visible if the picture was taken infinitely far away from the planet, which is not the case here. So the diameter calculated here is actually a bit smaller than the true diameter. But it's an acceptable approximation that actually isn't going to matter in the end. So, after the cross product, we get that the diameter of Auraxis is 14.7 kilometers, so a radius of 7.35 kilometers. It's not big. And that was to be expected, as continents are only a few kilometers wide. While we could stop here, there are issues with this result. It seems impossible for such a small celestial body to have a gravity as strong as the one we experienced in-game. So let's look at the density of Auraxis. How do we calculate density? Well, density is simply mass divided by volume. Here the volume is very easy to calculate. It is simply the volume of a sphere. And since we just calculated the radius, we immediately get the volume. However, mass is a bit tricky. How do we calculate the mass of Auraxis? What we can do is use the strength of gravity on Auraxis. In my previous video, I did an experiment to evaluate just that. I won't go in details over it again. If you want more details, you can go watch that other video. Here is the quick rundown. I have this formula that says gravity is equal to 2 times height divided by the fall times squared. Climbing up to 100 meters and falling in 3.14 seconds gives us a strength of gravity of 20 meters per second squared. So, how can we use this information to calculate Auraxis' mass? Well, we use the formula for gravity applied to a body, and it turns out there are two formulas for that. The first is this: mass times gravity. This formula is typically used for a body sitting at the surface of a celestial body, like a planet. The second one is Newton's universal law of gravitation. Anything that has mass generates gravity, and this law allows us to calculate the attraction between two bodies due to gravity. Let's look at the formula. Big G is the universal constant of gravitation. It's just a number. Big M and small m are the masses of the two considered bodies, and d is the distance separating the two bodies. Quick side note again. In our case, the distance d corresponds to the radius of the planet. For those who want to know why, this is because the planet is a sphere, and according to Gauss's law for gravity, studying the gravitational field of a sphere is equivalent to studying the gravitational field of a point at the center of that sphere. So, how do you use these formulas to help our case? Well, for an object standing on the surface of the planet, these two forces will actually be equal. So we put the two formulas equal to one another. Importantly, the mass of the object cancels out to only leave the mass of the planet. Rearrange the expression and we get this: mass equals gravity times radius squared divided by the gravitational constant. Perfect! We know the radius and we know gravity, so we just plug the numbers in and we get a mass of 1.6 times 10 to the 19th power kilograms. Alright, so far so good. Now that we know the mass and the volume of Auraxis, we can calculate its density. Let's plug all the numbers into Wolfram Alpha and we get a density of 9.6 million kilograms per meters cube. How much is that? It's a lot. For comparison, Earth has a density of 5,500 kilograms per meters cube. So Auraxis is more than 1,700 times denser than Earth. Moreover, the densest material that we know of, osmium, has a density of 22,500 kilograms per meter cubed. Auraxis is still 425 times denser than that. Also, Wolfram Alpha, who is much smarter than I am, automatically tells me that the density of Auraxis is on the same orders of magnitude as the density of a white dwarf. And white dwarfs are the remnant cores of ancient stars. It's absurd. So, this tells us that the radius we calculated doesn't really make sense. We need something else. When calculating the radius of Auraxis, we used the total length of Hossin. But if we look at Auraxis again, you will notice that Hossin doesn't look like it does on the map screen. So the original assumption that the map of Hossin we play on is the entire continent might be wrong. meaning that we cannot calculate the radius of Auraxis using the dimensions of Hosen. Let's use another approach then. Remember the formula for density? Density equals mass divided by volume? We also add the formula for the mass of Auraxis. Mass equals gravity times radius squared divided by g. And the formula for the volume of a sphere is this. If you plug the two latter formulas in the formula for density, you get this. With a little bit of calculus, you can actually isolate the radius, so you finally get this equation. So, now we have an equation that gives us the radius by only knowing two parameters, the strength of gravity and the density of the planet. We already know that the gravity equals 20 meters per second squared on Auraxis, so we only need the density. To try to anchor this in reality, we will assume that the density of Auraxis is the same as the density of Earth, so 5,500 kilograms per meter cube. Plug the numbers in and you get a radius of 13,000 kilometers. This is massive. This means that Auraxis is 2 times larger than Earth. It's mad. So this is it, right? Well, not quite. There are a couple of problems with that result too. First problem is that a rocky planet this large most likely wouldn't have the density of Earth, meaning that this result directly contradicts the assumption we made to obtain it. Indeed, the density of such a large planet would most likely be higher because the added mass would cause the planet to compress under its own gravity. The second problem with this result boils down to what Auraxis is, because Auraxis isn't actually a planet, it's a moon orbiting a gas giant, and during the formation process, such a massive moon would spiral towards the planet quite rapidly, well, rapidly on a cosmic scale that is, to finally just disintegrate, leaving no time for life to evolve on it. So, how big is Auraxis? Well, I don't know. No matter how you look at it, there is something that just doesn't click. Which is fine, it's not surprising, we are talking about a sci-fi moon in a video game after all. Yeah, I know, it's a bit anticlimactic, but that's how it is sometimes. If you have any other idea on how we could calculate Auraxis' radius, feel free to tell me. In any case, if you enjoyed the video, feel free to subscribe and like the video. You can also check my Twitch channel out. Thank you very much for watching.